Hey guys, so in today's lesson, we're going to be studying cooling curves, which are, uh, well, you know what, they're the opposite of heating curves. So basically everything that you learned in yesterday's lesson will apply in this lesson as well, but we will need to reverse all of our logic. I'll try to make this one quick. So we will have a homework associated with this lesson. You would have copied it down on yesterday's classwork. But for today's classwork, I do want you to change the aim to what are cooling curves and copy down these particular GNL questions and have them ready for me in class tomorrow. So this slide is about the energy and phase changes involved with cooling curves. Remember, temperature is defined as a measure of the average kinetic energy of a substance. It is not the same thing as energy because it is not measured in joules. It's simply a measurement of average energy. So the other type of energy that substances have is potential energy. And when substances cool down, they're actually losing energy of both kinds, that is kinetic and potential energy. So you would notice probably the kinetic energy being lost more than the potential energy, because you would notice that the substance is getting cooler to the touch as it loses kinetic energy. However, as substances cool from the gas phase to the liquid phase to the solid phase, they're also losing potential energy. That is the energy that is stored in the distance between molecules. So what does a loss of each kind of energy look like on a molecular or atomic scale? For kinetic energy, the loss of that kind of energy is going to look like the particles are vibrating with less motion, because kinetic energy is the energy of motion. So as substances lose kinetic energy, the particles will vibrate less and less. And as substances lose potential energy, you would notice that the particles are moving closer together. So as they condense from gases down to liquids, down to solids, the particles are getting closer together. So I added a particle diagram for you just to set a good example of how to draw particle diagrams. This is my gas phase. Liquid, it is allowed that the particles be touching, but they shouldn't be in a regular geometric pattern. And then for the solids, they do need to be touching, and they need to be in a regular geometric pattern. The process of cooling, as you may have guessed, is exothermic, meaning that it is releasing energy as it cools. So what happens to the energy that is lost by the substance? It is simply transferred to the surroundings. So as the substance cools down, its surroundings will heat up. So as we talk about phase changes, we need to use the right terms. They will be very similar to the ones in heating curves, but in reverse. Freezing and solidification is section DE. It is what happens when liquids change to solids. And it also has a synonym with fusion. So fusion is also the same thing as freezing and solidification. Likewise, condensation and liquefaction are here. It's what happens when gases change to liquids. Condensation and liquefaction are the opposite of boiling and vaporization, but unlike the reuse of the term fusion in this phase, people rarely would call this vaporization as you go in reverse. However, we will have some equations in future lessons that will be called heat of vaporization, and it'll be the same as section BC. The cooling curve below compares to the diagram of a heating curve in that it's simply flipped on its vertical axis, and it starts with gases and represents the uniform cooling of a gas until it becomes a solid. I do think that you should probably sketch this diagram with the things that I've labeled on it for your notes. Potential and kinetic energy change in cooling curves as well. And this graph is showing a substance that is cooling constantly over time. The line segments that represent decreases in kinetic energy are AB, CD, and EF, and we know that because those are the segments where temperature is decreasing, and temperature is analogous to average kinetic energy here. Similarly, the line segments that indicate changes in potential energy are the ones where kinetic energy is not changing. So that would be section BC and section DE. And related to that question is this one, which line segments represent phase changes? Because phase changes are really only occurring when potential energy is changing. And just to recall something that you heard earlier in the lesson, the closer particles get to one another, the less potential energy they'll have. So also, the closer particles get to one another, the more their phases are changing. So as you go from spaced out gases to relatively close together liquids to geometrically and well-packed solids, you're losing potential energy at each stage because you're losing the distance between the particles. And I have a true or false question. Kinetic energy changes during phase changes. I suppose it's a true or false statement. During phase changes, kinetic energy does not change, so I'll say false. And if you need evidence for that, you can see it right here on the graph. My phase changes are marked in red, BC and DE. And during those areas, you can see that the energy in terms of temperature, the kinetic energy, is not changing. So during phase changes, kinetic energy actually is constant. All right, so this graph is really just about the phases of matter in these diagrams. The line segment that represents solids only is line segment EF. And the reason for that is because the area that I'm indicating here, point E, this is the last appearance of a liquid. Put another way, you know that we have liquids here. So liquids are cooling down, and then this is the time period where the liquid is changing into a solid. And by the time it gets to E, that's the full transition of liquid into solid. So EF is going to be the only line segment that contains solids only. So going from there, you can see that the line segment that represents liquids would be CD. My reason why, I guess I would say that it's between AB, which is clearly gases, and EF, which is solids. Segment AB is the segment that represents gases only, and gases are transitioning to liquids from B to C. So at point B, you'll see your first bit of liquid, and at point C, you'll see your last bit of gas. So at point C, it's all liquid. But at point B is the last time that you will have gases only. So the line segment that represents condensation is the line segment that includes the transition from gases to liquids. So it would be line segment BC. And the line segment that represents freezing would be the segment that includes the transition from liquids to solids. So it would be segment DE. And we have reached the cooling curve summary, which we will treat as the pair-up. Please do copy this underneath the Do Now questions on the classwork page for this lesson. We'll do this in class tomorrow, no need to fill it in. And of course, copy down this summary, including the diagram, but don't answer the questions just yet. We'll do them in class when I see you next. Thank you for listening.